Today, here in the Queen Charlotte room, we've got George Malamidis doing a talk on load testing distributed web services. So George is currently the Vice President at loveholidays. He's been working there for about the last 5 years, which means he's one of the few people that's able to say that he uses the power of Go to send people on holiday, which in my opinion is very obliging of him. Additionally, while I was doing a little bit of speaker prep and having a look into everyone's backgrounds, I would recommend, if you have a bit of a poke around online, you might be able to find his album as well. But with that, a big hand, please, for George Malamidis.
Thank you, and hello. Today we're going to discuss a system that we built at loveholidays to make sure that all of our other systems can scale with growing load. A little bit about myself first. I'm old, so this could take a while, but I'll summarize it. I started coding in the 80s on an Amstrad 6128 as a child in BASIC, like the Netflix show Stranger Things. Many years later, my first job was here in London for a music startup that doesn't exist anymore. And I remember specifically my first day at work. It was installing Linux on a desktop, followed by installation of Squid. And I'm looking around to see how many people know what Squid is. It's a proxy / cache. A few years later, I would say got bettered by Varnish. After that, Varnish became the heart of Fastly, which is one of the most popular CDNs out there these days. In fact, we do use Fastly at loveholidays. And yeah, that's me having lived through 3 generations of caching technology. Many years and many jobs between my first job and loveholidays, including a stint at a consultancy called ThoughtWorks, where I met many people that I'm still friends with. Some of them are still colleagues with. In fact, one of them is here in the crowd today. That's Stu. Hi, Stu. And before loveholidays, I spent 9 years also, like the keynote speaker, at a HFT, high-frequency trading, low-latency, algorithmic sort of trading programs. It was a really fun time. And then things changed 5 years ago. So loveholidays is what in the industry is called an online travel agent, and we specialize in packaged holidays. So a package is a hotel and a flight, and some other things like which we call ancillaries, like a transfer from the hotel to the airport, car hire, that kind of thing. We are the 3rd biggest OTA in the UK right now, the biggest in Ireland. We recently launched in Germany, and we are on track to send 4.9 million people on holiday in 2024. So statistically, some people in the audience probably have booked with us, and I hope you have a good experience on your holiday. It's usually good. When people ask me why I do what I do, my answer is usually it's because I like solving difficult technical problems with other people who like solving difficult technical problems. So about 5 years ago, when another friend from ThoughtWorks, Mike Jones, gave me a call to say, hey, I just joined this place called loveholidays as CTO. Are you interested in coming along to take them to the next scale? The next level of scale. I was like, I don't know, a website, it's going to have a database, it's going to have a couple of web servers. I'm kind of writing, programs that trade 1 million times a second. It's probably not going to be that much fun. Boy, was I wrong. So let me try and explain that a little bit. This graph shows the number of holiday packages that we process aggregated by year. Can you see the y-axis okay? That's usually the type of number that happens when you fat finger something on a calculator. Who can read that number for me? Come on. No one from loveholidays. No one's brave enough to read it, or? So that's 1 quadrillion packages that we will have processed by the end of the year. That's not, that's CERN and astronomy numbers. Do you know how many stars there are in the Milky Way? It's way less than this. They're in the billions. This isn't a talk about package holidays, so I'm not going to explain how that number works out, but please trust me, it's real. And if we have enough time at the end for questions, if anyone's interested, please ask me about it, and I'll explain how it works. It's quite fascinating. If not, I'm also going to be at the conference for the next couple of days, so happy to talk about it then too. So, a lot of data. An interesting aspect of our website is an unbounded any search. What that means is that customers can search for holidays without entering a date range and without entering a destination. And they can also sort the results in various ways, let's say by price or by popularity or friendliness for families. Now that you understand the space, we're talking about trillions of packages that we're searching across. We want in real time to be able to search and sort all of those with requirements that are displayed in this graph. The blue line is our P50 latency in milliseconds, and that's about 30 milliseconds, and our P99 is 200 milliseconds. Quite an interesting challenge. What's particular about our use case is that the load that hits our servers is variable. We don't get constant load all day long. Turns out people don't buy holidays as much in Europe at 6 in the morning, neither do I at 1 a.m. But things peak at around 9 every day. Load is also seasonal. Way less people buy holidays in December because they're having fun and going to Christmas parties. But then depression kicks in on Boxing Day when you're hungover and it's dark and you're with your weird uncle. So people start buying holidays. What this means for our systems is they have to deal with a lot less load in December, but then there is this period that we call peaks in January when people give our systems a run for their money. How do we deal with this? Because we want to be efficient. There's always a strategy where you can say, figure out what your peak load is, provision for that, and run at that rate forever. That is not the most efficient way of doing it because a lot of the time you're paying for resources that you're not using. So, I imagine a lot of people in this room, we use Kubernetes and we make use of Kubernetes horizontal pod autoscaler. So what you see in this graph, the blue line you've seen already, that's throughput during the day. The red line is the number of pods that we spin up based on, in this case, CPU load. So we only use the infrastructure that we need. The result of this is that our CFO loves us. Our systems are very efficient, and this graph shows a metric my colleague Dimitri has come up with it, which is stakeholder clickbait. It's how much how much it costs for us to serve 1,000 sessions. And what it means is that our systems become more and more cost efficient the more traffic we have. Because we don't need to pay linearly with traffic, our costs are actually sublinear. The more money the company makes and the more people that we actually send on holiday, the cheaper it's for our systems to serve that traffic. That's not enough, though. That's just a number by itself. It doesn't matter if your infrastructure is cheap, if it goes down all the time. So we have requirements, high reliability requirements. You can't see it here. Maybe I should have used a different scale, but we're at 4 nines, usually. Our systems don't go down a lot. I've just been speaking to Matt. I don't know if Matt's in the audience. Hi, there you are. Hi, Matt. The last time we had serious downtime was a couple of years ago 40 degrees in London. I don't know if you were here and if you remember it. Everybody went insane. So did GCP. The GCP data center melted, both the one in London and the one in Belgium. We almost stayed up, but not quite. We prepared for the next Armageddon, but that was the last time. So all of these things together, maybe I'm making them sound simple because we worked very hard on making them sound simple, but it wasn't easy getting here. So you read this. I don't like reading from slides. We want to know our systems can scale, and we don't want our customers to find out for us when they don't. Quite similar to writing tests, where we are trying to simulate what the real world is going to be doing with our systems, like unit tests. Load tests can serve the same purpose. They can simulate what customers or users or other systems can do with our systems to make sure that they don't go down when they do something funny. So this is load testing, and I think from university to writing to research to statistics, when you're trying to do something, the first thing that you should try and find out is if somebody else has done it before. I know this is a little bit hard for us engineers because we enjoy building stuff a little bit more than we enjoy using stuff. And I'm definitely guilty of that. But I tried to curb my personality. And when we started looking into this, there's a lot of really great tools out there these days. K6, acquired by Grafana. We were having a chat about it last night. This little guy here is Vegeta. It's another tool written in Go. We still use it at work, and we heavily inspired what I'm going to be talking about. There's good old HTTP perf, there's AB. Long story short, we tried all of these things and ended up writing our own in the end, but at least we tried. The reason we did that is we want user-realistic load tests. All of the load generators that I'm familiar with, and things might have changed because I haven't checked since 2 or 3 years ago when we wrote the tool that I'm going to be talking about today, most of load generators say, here's a request, or here's a script of requests, play them at, let's say, 1,000 requests a second. On a complex website with millions of users, that's not how it works. Users can do crazy things that you can't predict. Traffic can ramp up or down. It's not very realistic to just say, hit this endpoint 1,000 times a second and see what happens. It's similar to writing unit tests. Like when you write a unit test, you are guessing what someone is going to do with it, and you need to think of edge cases. Who uses GoFuzz? Fuzz testing? 1 person, 2, come on. Really? 3, thank you. Come on, more of you should be using it. But it might become obsolete with AI, but what it does is it creates scenarios that you didn't anticipate so that you get greater confidence that your systems can actually deal with unexpected things. Our use case is similar to that, but for load testing. How can we know what customers are going to be doing with our website when all of them decide to book, the same destination because they saw something on TV, let's say? This is a super, super high-level version of our architecture. There's like a round-faced customer going into our CDN, Fastly. That goes into Nginx, which serves as a reverse proxy into our front-end services, which then call our back-end services. What's really interesting here is we log everything into Grafana log key. All of our CDN logs go there. All of our services log there. There was an interesting question at the previous talk that I attended about debugging. It also talked about logging, and what the question was, is it very expensive to log everything? For us, it's actually dirt cheap because we host Loki ourselves. And in fact, we have blogged about how we can store terabytes of logs every day for peanuts. What's interesting here is Nginx, which sees all the traffic that goes to our services, logs every request as an access log, which goes into Loki. And that is a record of what customers are doing with our systems. Enter this little thing that we built that we call Albot, that streams logs from Loki into a little Go application, and this is our own custom load testing tool that then replays them against systems. The key to replay is that when it reads a line from an access log, it will record what the timestamp is, and then when the next log comes along, it will subtract the new timestamp from the old one, which tells it how long to wait before replaying the request. So you get to replay exactly what users did, and then if you want to go harder, you can replay that at multiples of the original recorded rate, hence the load testing aspect of it. We call it Albot because it hunts at night. Us selling holidays in Europe means that our systems tend to be quiet at night, which gives us a convenient opportunity to actually test against production, which is quite fun. It can be a little bit stressful when you first start, similar to doing chaos engineering, but then the level of confidence you get something out of that is pretty high because you know exactly, you're testing the actual system that you're trying to understand, the performance of. So this graph is a throughput graph. You can see that the traffic that hits our systems at 3 in the morning when Albot's hunting is a lot higher than normal traffic. So inside Albot, there's Ripley, and we're going to talk about Ripley a little bit. Let me give you a second to take a photo so you can all download and build it and give it a spin. This is a very simplified version of how you can call Ripley. It expects requests in JSON lines format. That's just JSON, one object per line. And the pace flag tells it to, in this case, run those requests for 10 seconds at 1x the rate. So this is pretty much replaying exactly what happened. Then for another 10 seconds at 5x the rate, this is trying to say, what if 5 times the customers hit our website? And then for 1 hour at 10x the rate. And you can go as high as you want. But if you're doing it in production, and you haven't done it before, be careful. This is useful for us to simulate real traffic that matches our scenarios. Our traffic never spikes like this unless a scraper or some malicious DDoS attacker actually manages to make it through a bot protection, which I'm not going to jinx it too much. It doesn't really happen. So traffic ramps up, and if you remember the graph that showed the number of pods, auto-scaling, it's not a plug-and-play thing. You have to tune it. And in order for us to tune it, we want to simulate what customers are doing, and customers usually, traffic starts ramping up slowly, and this is what allows us to do this. So we say that our pace parameter is a lot more involved than this one, but it results in this. We start with actually less than 1x the pace, because when Albot starts running, our pods are at the minimum they could ever be, because no one's using the systems. And then slowly ramp up all the way to 5x these days. Replay worked very well from the first day we put it into production. We started building the system in November in anticipation for the peaks that I mentioned, peaks being January. So we built it. By the end of November, we started running our bot against our website at 10x, and then we survived peaks like champions, and it was great. One thing that we noticed, though, was even though that we were shooting for 10x, we were actually not hitting 10x the load. At this point, we hypothesized that Ripley wasn't keeping up. So this is the optimization part of the talk, even though I'm not going to go into deep coding details. We created a test harness to prove the hypothesis, and our expectations were we downloaded 10 minutes of logs. So because the logs are for 10 minutes of traffic, if we replayed them at 1x the rate, it should take 10 minutes. If we replayed them at twice the pace, it should take 5 minutes. At 10x, it should take 1 minute, and so on. And this test went up to 160x, which, to put absolute numbers next to it, if our search engine throughput was 300 requests a second times 160, it's in the tens of thousands of requests per second. This is the result of the test. It actually shows that even at 1x, and you can't see it, this kind of logarithmic scale was the best way I could show it, but even at 1x, even though Ripley kept up and didn't die and actually finished, it always took a little bit longer. It always drifted. So at this point, we started speculating. So I'm going to Ripley parses JSON. It also has an HTTP client. Who thinks it was the JSON parsing that was messing it up? No one. Okay. Who thinks it's Go's HTTP client? Good. Good, because it was none of them. I was expecting some people to actually volunteer so I can reprimand them. But you're passed. Yeah, it was none of those things. And really the answer is, you don't know, measure it. Profile. And this is what we did. By doing that, what we discovered was, first of all, read this. It's code. I'll stop talking. Does it make sense? We're just saying between requests, when was the previous request, when's the request now, find the difference, sleep for that amount of time. And of course, the algorithm doesn't look exactly like this, but this is more or less what it does. And there's other code. This was the interesting thing. The other code also takes time to execute. And it can be nanoseconds, but when you're writing things at 10,000 times every second, even nanoseconds add up that create a cumulative error. And that's why even when we were running Ripley at 1x with 10 minutes worth of traffic, it was taking 11 minutes to finish. Of course, the signs were all in the profiling, because when we profiled Ripley and we were expecting to see, high GC rates because the JSON parser is not efficient with memory and you should use fast JSON or easy JSON, or because the HTTP client makes too many allocations and you should use fast HTTP, it was none of those. Ripley was not CPU bound. It wasn't GCing too much. It was all going well, and it was actually our algorithm. So how did we solve this? We solved it by introducing the concept of a wall clock. We actually recorded the time every time a new request was supposed to be played. So we knew exactly what the drift was. So our new algorithm actually compensates for the latency introduced by the code around firing each request. And then that was proven by this beautiful graph. There's two lines. There's the blue line that says how much you're expected to be taking, and the red line is how much it's actually taking. We managed to be bang on, up to 80x, and we kind of missed the mark when it comes to playing it at 160 times the rate. That's supposed to finish 10 minutes worth of requests in 3.75 seconds, and it takes about 6.5 to do it. So there are 3 seconds in there that we haven't accounted for, and at this point, we might actually want to be looking at allocations or CPU, but in our use case, we never take our systems up to 160x. 80x is more than enough. So now it was time to try this in production. Did it work? Huh? No one wants to say, because everyone learned not to answer now. Of course it didn't. We were testing on our laptops, and conditions were different. But, you know, that's to be expected. And there is a lesson there. Measure, understand. You can do that in production. You can do it anywhere. So we started trying to think of what the difference is between production and local development. Our first hypothesis, because at this point, you know, we've been with this system for long enough, our guesses are starting to become relatively accurate, was that when we were testing locally, we have a purpose-built web server that's like 3 lines long that all it does is responds with no op. What that server has is stable latency, and it's also fast, so it can keep up. Whereas our production systems, even though they are quite stable and they are quite fast, they're also variable. So now we started thinking maybe Ripley can't keep up when it tries to you know, hit systems that are not as fast as it is. We started profiling again. It was my first time actually into Go routine profiling, which I found super interesting. And it's actually not the easiest thing in the world to get documentation around how to do that. Because usually you see the result, you get stories about how to profile for memory, how to profile for CPU, network, disk I/O, but you can also profile Go routines. That was fruitless, though. That wasn't a problem. At this point, we had also added specialized logs in Ripley just to let us know how much skew the algorithm is introducing to itself. And the answer to the problem is way less fancy and way less scientific than you might be hoping for at a conference talk. I was pairing with one of my colleagues on this problem, and another one of my colleagues who's actually here right now. Hi, David. Was sitting behind us, at the desk behind us, and overheard us talking about it. And he said, what about the default number of connections in the HTTP client? Like, I mean, cool. We have a whole test harness set up. Let's give it a try. We tried it, and it worked. And we went back to measuring. We tried this in production. Did it work in production? Come on. One person nodding, good. You win a hoodie. Thank you. Yes. So this is what Ripley looks like now, running up to 40x and 80x. It's a little bit funny that the drift is negative. I think you can imagine why it is negative. We're doing some clock math ourselves to compensate. However, it's so minuscule that it doesn't really matter. This is a great result. So if you ever decide to do this yourselves, a few things to remember. You can replay incidents. This is extremely powerful. I don't know how many times you had to deal with an incident, and then you made some changes, and you waited for customers to hit your website the next day, saying, oh, did it work? If you're lucky, it did. If not, put more logging, see what's happening, distributed tracing, all of the tricks. But the feedback cycle is quite nerve-wracking because you can't actually do it when you want to. You have to wait for real traffic to actually do that. And that's if you're lucky and conditions are met again. With your access logs, you actually have a recording of exactly what happened that triggered the incident, at least in terms of what users were doing with the system, because, of course, you might get like some random network failure or one of the pieces of hardware that support your infrastructure had a hiccup that had like a compounding effect. That one, you know, we can't help you with that yet, but this is extremely powerful, and if you have an actual incident, then even in a controlled environment and not production, if your staging environment happens to be similar to production, then you can apply the fixes, replay the incident, and see what happens. And at least, you know, that night you can, you know, go back and watch. I'm going to plug Stranger Things again. House of Dragons, without having to worry about the systems. We replay traffic at multiples of the original rate, and we have a relatively busy website. Not Cloudflare levels, it's or Grafana levels. It's a completely different use case. But we also have a lot of suppliers. And our suppliers' technology is not necessarily thought through the same way that we think through our own. So if we let Ripley loose on their systems, at best, they would be very mad at us. So just remember to do this. We actually prune our logs or filter them to keep out requests that we know can be dangerous to others or to ourselves. Which brings me to this one. If you're writing, if you're load testing against stateful systems, let's say you work for an online retailer and you wake up the next day and you have 4 times the sales, initially it's going to look great. But then less so. This is important too. PII, logs record everything, at least in our case, unless you have a very sophisticated system that automatically strips PII from your logs. Actually, do you? I'd like to know. I'd like to talk to you if you do. Okay. Cool. So, yeah, be careful with that, because there is a reason why it's personal, and there is a reason why it's actually illegal for most of us to be accessing it, unless we have a very good reason. So remember that load testing is going to be replaying it. More eyes and more systems are going to be on this data. Always remember to keep PII out of it. Man, I had brought a prop that I wanted to use to get your attention, and now the talk is almost over, but I think I still want to do it justice, because I started using Go, I think a bit less than 15 years ago. It was before 1.0 for sure. It was when I was at that HFT trading firm that I was talking about. And I must have been vocal about it. And my colleagues got me this OG gopher for present. It's the American great-great-granddad of the British guy. I want to say it's worth a lot of money. It's not, because it's got something that looks like a cigarette burn here. But I thought it'd be really cool that if we do another talk like this in 10 years, there's going to be someone in the audience who I'm going to tell that they're younger than my gopher. It was way cooler the way I had planned it. This brings us almost to a close. It's the so what moment of the talk. Like, that's a pretty cool, interesting, fun thing to do if you're an engineer. At Love Holidays, we have 5 engineering principles, one of which is technology is a means to an end. It means that we don't build systems for the sake of building systems. They have to do something. They have to do something for some customers or a business or a non-profit. It doesn't matter, but even though I do love building stuff for the fun of it and taking things apart so that I understand how they work, in this case, we wanted a consequence. So what this graph shows, and I realized because we're on GCP and we use G Sheets, all of my graphs look the same as the keynote graphs. The blue line is traffic in December, and then Boxing Day when depression hits and it gets really good for Love Holidays. So you can see traffic triples. This is just one of our services, and it's the y-axis is requests per second. And then the red line and the yellow line are the latency of our systems. We didn't have to do anything other than all of the things that I talked about. But when that happened, we could just sit back and watch our systems win a marathon that we trained for 2 years. So it was quite a good feeling. This is the talk. Cool. We can chat about things or give you back time. It's sunny outside.
Yeah, so hands up if you have a question.
A really interesting talk, thank you. Do you combine other techniques like chaos engineering with your replays to make sure it still stands up when other incidents are occurring?
Other techniques to ensure the systems.
Yeah, so you're replaying the messages.
Yeah.
But do you then do like chaos engineering type things, so start pulling down pods and clusters?
Not very often. Not very often. We've done chaos engineering a couple of times. We always wanted to do it more regularly, but then life happened, and we didn't do it again.
Okay.
We've done it on staging a few times. We didn't get the same excitement out of it. It does also serve a slightly different purpose, which is it's training for engineers rather than anything else. But certainly in this case, our architecture has been informed by these tests. We make sure that horizontal pod auto-scaling is what it's supposed to be. We make sure that the number of replicas and where the replicas are located give us high availability. Over time, these days we have canary deployments, which is also very useful. Not very related to load testing, but it means that if we release something that triggers an alert somewhere, then that, first of all, we only release to 10% of the population, and then that gets automatically rolled back. There's a lot to do with reliability that we do, but not necessarily in a similar vein as load testing. For that, we have normal CI/CD plus these load tests that just run every single night. And we have had mornings where we turn off our pager duty between 11 and 7 because we don't trade enough to warrant waking up engineers. But there are times when we wake up at 7 and we will get paged because our bot messed up the website, and then we'll go and look at what went wrong and fix it before someone who wants to book their holiday does.
Cool, thank you.
Thank you for your question.
Next question.
Hi, great talk. Thanks very much. I was just wondering, you touched on that sort of any-to-any search that was, it's obviously quite fast, you're doing it at 200 mil. Just wondering if you can sort of touch on how you're sort of optimizing that in Go and what tricks you're using to make it that quick for that such broad parameters there.
That one is actually written in Java, not Go. That doesn't mean it can't be written in Go. it is bespoke. We replaced Elasticsearch and Solr with it. It is, you have to come and work at Love Holidays for me to show you, because it's something none of our competitors can do, so it's intellectual property that we try to keep a little bit secret. I mean, I can give you generalities around, you know, don't allocate too much, but it's really the algorithm and how we built a bespoke search engine that is designed around the domain of holidays rather than a hash table or that kind of thing. I hope it's not a very disappointing answer, but you know, there's the QR code on my left will tell you that. You can find that.
Brilliant, thank you. Okay, next question.
Thank you again for the talk. So when it comes to load balancing, you mentioned you took out the external APIs. If you were to include them, how would you suggest load balancing when there are failures? And yeah, just basically random failures occur, they spike, they go down, and yeah, just load balancing that.
Let me understand the question. So you're talking about our supplier APIs?
No, more so load balancing and taking into account that if there were external APIs used, they could fail. The system has to handle it. Loads could still be increasing.
Okay.
Errors could be increasing too.
Cool, I get it. Kubernetes takes care of a lot of that for us. So if there is a pod that is misbehaving, Kubernetes already knows to send traffic to other pods. Then we also use a service mesh called Linkerd, and Linkerd also has smarts around directing traffic based on several health metrics. Another common pattern when requests fail, retries. Retries, if done without much thought put into them, they can cause more trouble than they can avoid. Because, have you heard of thundering herd issues? So when a service slows down and the consumer times out the request and retries, unless you back off, you end up doubling, tripling, quadrupling the traffic. So you're making things worse than better. So Linkerd has the ability to do that in a more sophisticated way for us, but also most retry network libraries allow you to tune retrying to deal with problems like this. I assume, because you mentioned load balancing, you're thinking of one service that has multiple replicas, and that's what I try to answer. If all the replicas of one service go down, then that part of your infrastructure goes down, and then you either have to harden your systems so that they work without whatever that service is providing, and if what that service is providing is, you know, access to a hotel, in our case, then forget it. It's not going to work. But we have a service that prices requests and works out our margin. We have bespoke code that will use a failover calculation if it can't get to that service. So that's another level of failover that we can give our applications, but that's bespoke to the specific utility of that one service. Did I answer your question, or?
Yeah, thank you.
Thank you.
Okay.
Thanks again for the great talk. You mentioned that you're running Ripley on a nightly basis. Do you find that you're surfacing enough issues that it offsets the cost of the compute?
Yes, definitely. From the perspective of it's not just for regressions. It's for the graph that I showed that goes like this, and it's our cost per 1,000 sessions. we continuously tune our services to have the right levels of HPA, use the correct type of a CPU. We run on GCP, so you can buy the most expensive one if you want, and then you get a lot of bang for your buck. But having replay in place and having our production systems in place and measuring how much of their resources they're actually using, then we can tune our spend. And that's, yeah, that's one big benefit. I think with performance, it's quite rare that you would, especially if you're disciplined, that you would deploy something that makes a service twice as slow as it was yesterday. And the difficulty is when you introduce very little latency, 1 microsecond at a time or 1 millisecond at a time over 9 months. We have SLOs in that case. And our SLOs, the budget will burn, but also we don't want our P99s and our P50s to ever go above a certain level, and we get notified when that happens, and then we go and figure it out.
Thank you.
Anyone else?
Hi, thank you very much for the talk. I had a question sort of relating to the distributed nature of the architecture and how load testing affects that. So if the access logs are kind of driven by what the customer is doing in the front end, the back-end APIs that it talks to may internally talk to external systems, not necessarily during a write request, but it could be a GET query that, I don't know, fetches a particular supplier's information to give you that in the search results. And because we're testing against a production system in this case, are there ways of mitigating how often we talk to that production client, knowing that it's on a production system and the only way we know we're making the requests is that there was an access log from a customer that did search this, and downstream it eventually calls that external service?
We know from the URL that somebody hit from our website that hit Nginx, eventually which system will get called. And to be double, triple, quadruple safe, what we do is we maintain a whitelist of things that Ripley is allowed to replay. So the way the process works is we download all the logs from Loki, then we filter them through that whitelist, and that's how we're sure that we never replay anything that can cause something that it shouldn't. We might have had one case where that didn't quite work, but it wasn't anything catastrophic. I might be making it up, yeah, but having a blacklist is annoying because you have to keep it up. It's not the most automated thing in the world, but it's the closest that we got to, you know, being extra careful and super safe about this. Was that what you were asking?
Yeah, that answers it.
Thank you.
Thank you.
Next question.
So you've covered a large part of covering your own scalability, but having downstream providers, your scalability will still be linked to that dependency.
Yeah.
So I know this is maybe a bit off topic, but how have you handled graceful degradation or kind of trying to handle that and the impact it would have on your brand and also potential loss in revenue by having providers that you've gone through a process of onboarding, using, relying on, but can't scale to the levels you need to?
4 of the 5 people sitting behind you, that's their day job. They work for our supply team. I'm going to try and do it justice, but these guys have come up with an architectural pattern that we call edge services. An edge service, in our case, is something that sits at the edge of a network. It's something that communicates with a supplier. By doing that, we localize the blast radius of one supplier going down. So when that happens, the applications know how to ignore it. And if you think of our use case, we get a hotel from many suppliers. A customer gets back the best results from that hotel. If one of the suppliers is too slow for SLAs or goes down and they keep returning 500s or we keep timing them out, then we take them out of circulation. And then, of course, there's a lot more domain-specific bespoke logic that we have around that. It used to be a problem before our supply teams started working on this because, as you can imagine, 12-year-old company, when we joined, it was a startup, extremely successful. You can tell what the systems and the code bases were like. Conway's Law, one big team, everything's one big thing. One thing becomes slow, everything else becomes slow. Over the 5 years, we tried to address this by distributing our services based on logic like the one you described. And of course, there are libraries and tools out there that, like the discussion that we had about retries, you can do that with external APIs as well. And of course, Go is quite good at this. In Java, it's a bit more of a pain in the ass to make things reactive. Essentially, you don't want any long-running connections to be eating up your memory. Do that when you're talking with supplier systems. Use something that uses an event loop. It's like the 10K whatever problem that I say it like it happened yesterday, but I'm old. But it goes to show that it's a solved problem. And you know what I mean? Yeah. I think Nginx was the first one to popularize the event loop and lightweight networking. Thank you.
All right, next question. No one keen? Got another almost 10 minutes if you'd care to use it.
Thank you. Very good audience, albeit a little bit shy with the questions. But yeah, nice meeting you. Thank you.